Okay, guys, so we'll talk about mathematical induction today, um, and then in today's class and next class, we'll continue mathematical induction. So the worksheets for this class and next class is going to be handwritten. It's not going to be on Python. So mathematical induction is a relatively challenging topic, so make sure you solve the worksheet and make sure you're present in the class on the chat session or the discussion session on Canvas during class time, and ask me any questions anything that is confusing you. Okay, so let's start. So induction is just a method of proving a mathematical statement. So, and it's related typically to elements of a sequence. So you'll typically be given a statement, a formula, and then you have to follow some particular steps, which we'll discuss in the next few slides to prove that mathematical statement. In mathematical induction, there's usually a base case, right, which basically establishes the theorem for the first value in the sequence, right? And then you always start with the base case, and then you do the inductive step. So now this is an important step that you have to do to prove a statement or a theorem using mathematical induction. So the idea behind this is that if the given statement is true for any value k, or any positive integer k, it has to be true for any value k plus 1. So if it's true for k, it has to be true for k plus 1. So it's in other words, it's a continuity. It's a statement of continuity of the theorem. So if it's true for k, it's true for k plus 1. The theorem has to be true. Now let's do it in a bit more formal. Let's describe it in a bit more formal way. So let's say that S of n, right, is a mathematical statement, a formula that is given to you, and it is it is given for positive integer, for any positive integer n, right? Now you have to show that the given mathematical statement is true for all positive integers, right? And the way you do it is that you start with a base case. So this base case is when n is equal to 1, right? So that's your base case. So you show that the base case is true, right? And then you move on to the inductive step. Now the inductive step is going to correspond to all positive natural numbers, right? All positive integers, sorry. And so this plus sign means that you're dealing with positive integers. And then you say that you start with S of k, you replace n, so this is n equals, you replace n by k, n equals k. And then you show that what your statement, your theorem, right, is true for k plus, when you replace n by k plus 1, right? And we'll see how this is done. So this is called the inductive step. Okay, so let's look at the flow of how the proof goes. So you first show that p n equal 1 is true, so p of 1 is true. And then the idea is that what does this mean, right? P of k implies p of k plus 1. So for k equals 1, if p of 1 is true, right, this is the base case, then it implies that p of 2 is true because of the inductive step, right? If p of 2 is true, then p of 3 is true, and then p of 3 is true, p of 4 is true, and so on. So this is that part where the proof, it continues. It's like a continuity statement that the proof has to be true for all positive integers. So let's look at an example. Now, this is an identity that's given a mathematical statement, as we said in the beginning. Now, this is the sum of a sequence. And we have seen that the sums of sequences can be given. You can explicitly calculate the sum, right, by evaluating the left-hand side, or you can just directly use this formula to evaluate the sum. And we've shown using Python that you can do both of these and show that both of these give you the same answer, right? So now let's look at the base case. How would we do the base case and then the inductive step? So now the base case is when n is equal to 1. So this is your n, right? So now you want to replace n by 1 on this side, right, and on this side. So this is what you're going to do. N is equal to 1. So on the left hand side, so now make sure you consider both of these. Now you have to show that left hand side is equal to right hand side, right? This is what you have to show. And so you'll first replace n equals 1 on the left hand side, right? So you notice that this we plugged n equals 1 over here. So there's just one term. So the sum is trivial. It's just one term. So you get 1, right? J equals 1 is the only term in the sequence. Now when you replace n equals 1 on the right hand side, you get this. So n times n plus 1. So this is your n and this is your n, right? So you replaced n by 1, and so you get that equal to 1. So it's just 2 divided by 2, which gives you 1. So we have shown that both this is your left hand side and this is your right hand side. So we have shown that the left hand side and the right hand side give you the same answer, and so this equality holds. Okay, so we have proven the base case, and so now let's move on to the inductive step. So now what you're going to do is you're going to say that, suppose that the statement is true for any positive integers n equals k. So now what we're going to do is you're going to replace n with k in this one, right? And so you get k times k plus 1. So this is just nothing other than just redefining the symbol. And now what you're going to do, so then for the inductive step, what you're going to do is you're going to replace n with k plus 1. So in this case, you're going to show that n equals k plus 1. For n equals k plus 1, this statement is also true. But that you have to prove, which is the we're going to do next. So you have replaced. So when you replace n with k plus 1, right? So k plus 1 over here. Don't forget the parentheses, right? I've noticed sometimes students forget parentheses over here. So n with k plus 1, and so you get n with k plus 1 over here, and then plus 1, right? So that basically becomes k plus 2. So what you get is you get k plus 1 multiplied by k plus 2 divided by 2, right? So that's the statement for k n equals k plus 1, which is this, right? So now you have to prove this. And how do we do that? So again, so be careful with these steps, because I've seen students getting confused with these steps. So let's go slow. So you're going to start with left hand side. So this is your left hand side. And what you're going to prove is that your left hand side, again, is equal to your right hand side. We did that for the n equals 1 case. Now we're going to do this for the n equals k plus 1 case. And so now this is called the inductive step. We're going to do the inductive step, which is so this is first we're going to separate out the last term, right? Now what do we mean when we say separating out the last term? So notice that this is your last term, right? This is when so last term is when j is equal to k plus 1, right? So you're gonna split the sum, right? You're gonna keep the second last term is j equals k, right? So you're gonna keep the whole sum and then split out the last term. So this is your last term, right? This is your last term of the sequence. Again, this is your last term. You're going to do that. So now, why are we doing this? We're doing this because we have to use this equation, right? This equation says that the statement, the mathematical statement that we have, is true for n equals k. And in order to use that statement, we have to separate out the last term. And the last term is when j equals k plus 1, right? So this is just like you're adding 1 plus 2 plus 3 plus 4. You're getting rid of the 4 and then just writing the sum. So let's say instead of so let's say that you have a sum like this, right? J equals 1, 2, 4, right? So I can also write this as j equals 1, 2, 3, right? And then plus 4. So 4 is your last term. When j is equal to 4, you split it out over here, and then the rest of the sum is just the sum with this reduced by 1 because you have removed the last term, right? So this is what we're doing over here. We're basically getting rid of the last term so that we can use an equation. So now this part, right? So this is where we use the inductive hypothesis. We're going to use this equation, okay? And so when you do that, you get you replace the whole sum with k times k plus 1 divided by 2. And after this it's algebra. If you you can always use Khan Academy and other sources to review factorization. So in this part, right, where you go from this to this, the proof, the last few steps, you would always need to do some algebra, and in particular factorization, right? So in this case, you see that you basically make the denominators common. You multiply and divide this by 2. So now the denominators are common. You bring them together, and so they're added together. So now in this case, what you're going to do is you're going to take the k plus 1, common, right? It's a common factor. You take the k plus 1 out of the equation, so you're left with k plus 2 in the parentheses. So this is what you're left with in the parentheses. And then you can see that this is exactly the right-hand side of our statement. So we have shown that we started with the left-hand side, right? And then we ended up getting the right-hand. So this is equal to right-hand side by using algebra. And so this is an example of how you would use mathematical induction to prove a mathematical theorem or a statement. So go ahead and download the worksheet and solve the question I gave you on that. Let me know if you have any questions.